Welcome to Study Loop.
For this problem, we're told that a cylindrical shell of radius a 0.06 meters has a linear charge density equal to 8.5 times 10 to the negative 6 coulombs. And then we're asked to find the voltage at different points in this configuration. So in order to find the voltage, the only thing we can find from this diagram is the electric field. So we need to find the electric field inside the shell. And so in order to do this, we need a Gaussian surface. So we just draw a Gaussian surface symmetric inside of this cylinder. On this cylinder, or on this Gaussian surface, we can then do the integral of E dot dA is equal to charge enclosed over epsilon naught. But since we're inside this cylinder, and this cylinder is simply a shell, the charge enclosed is 0. So therefore, inside everywhere, our electric field is equal to 0. Now we do outside of the Gaussian shell, of the cylindrical shell. So we have our cylindrical shell, and remember with Gaussian surface, we always want to exploit symmetry. So we just have a symmetric cylinder that goes around our cylindrical shell. We'll say that it has length L. Our Gaussian surface will have radius R. And then on this, we have the electric field is pointing radially outward everywhere. And as well, dA on the ends will point sideways, but dA will point radially outward on the sides of our cylinder. So on the ends of our cylinder, dA and the electric field are actually perpendicular, and so therefore the integral along those end caps of our cylinder will be 0. So we simply need to integrate E dot dA along the sides of our Gaussian cylinder. So Gauss's law will just become E times the area of the side of our cylinder, since the electric field will be a constant at a fixed radius. As well, the charge enclosed will simply be the charge density lambda times however long our Gaussian cylinder is. So that's just lambda L over epsilon naught. So now the side area of a cylinder is simply 2 pi r, or the circumference of a circle, times the height of our cylinder. So this will be E times 2 pi RL, and then this is just equal to lambda L over epsilon naught. So therefore, our electric field outside of our cylindrical shell is simply equal to lambda over 2 pi R times epsilon naught. Now we have our electric field everywhere in space, and from this we can find our voltage. So for part A, it asks us to find the voltage between 2 points. So we have our cylinder, and we want to find the voltage between a point on the surface and a point 4 centimeters above the surface. 4 centimeters. We already talked about how the electric field points this way. And so what we can do is we can do delta V is equal to minus the integral of E dot ds, where ds is a path integral between our two voltage points. So what I'm going to choose is I'm going to choose this to be an integral path of S that runs in the same direction as my electric field. So then what we have is we have V at our point minus V at our surface is equal to minus the integral of R at our surface, R at our point, of our electric field. Now here our electric field is completely outside of our cylinder, so we can plug in simply the electric field outside of our cylinder, which was just lambda over 2 pi epsilon naught r, and then this will be dr because our s is pointing radially outward. So when we do this integral, we can pull out all our constants. We have lambda over 2 pi epsilon naught times the integral of 1 over r, which is just the natural log of rp minus the natural log of rs. And now we can rewrite this to where this will just be equal to, so remember your natural log rules. When you have a minus, it becomes a division. And then I'm going to bring this minus on the outside in. So this will become lambda over 2 pi epsilon naught times the natural log of rs divided by rp, where rs was equal to the axis of the cylinder to the surface of the cylinder, and rp was equal to the axis of the cylinder all the way out to the point. So this will just be 0.06 meters, and this will be 0.1 meters because we have to add this 4 centimeters. And when you plug this in, you'll get a value of negative 780.085 volts. Now with part B, we're going to do something very similar. So in part B, they're just asking for the voltage between two different points. So we have our cylinder here, and they're asking for the voltage between the surface and a point 1 centimeters away from our axis. And so what we're going to do is the electric field on the outside is pointing radially outward, but remember the electric field on the inside was 0. So when we try to do a path integral connecting these 2 points, we simply have delta V is equal to minus the integral of E dot ds, but since the electric field is 0, this delta V is simply equal to 0. And that concludes for that problem.